Hello everyone, this is Monica Lupidon and today we'll cover unsteady state molecular diffusion. This is part of the course CE 318 Heat and Mass Transfer. This is the general content of my presentation. First, I'll give you an introduction and we'll also do a review of the different equations about mass transfer that we covered so far. Then we're gonna see what's the general equation in the case of unsteady state. And then we'll see two different approaches to solve this general equation. One is the analytical solution, and the second is the use of charts considering different geometries. If you recall, this is very similar to what we've seen in heat conduction. And finally, a summary. If you recall from previous classes, there are two main equations in mass transfer. One, the general equation of mass transfer is labeled here as 1, and it has different elements that we cover, as I mentioned in previous lectures. And the second main equation is the Fick rate equation, which gives us the relationship between the molecular flux of the element A with the diffusion of that element A, which is the first term here, plus the bulk flow, which is the second term in this equation of Fick rate. When we combine 1 and 2, along with the boundary conditions and the initial conditions, we should be able to get a solution. This is not that simple, and depending on the geometry and the boundary conditions and the initial conditions, the analytical solution of this system could be complex. That's why, as we're going to see in a minute, we can also use some graphical representation or graphical solution to solve these kind of systems. There is a third equation, which is not really a new equation, it's mass balance. But sometimes, depending on the system, we want to zoom out and do, let's say, a macroscopic mass balance. And this is equation number 3. We covered this in one of the cases in lecture 12 when we studied the general equation of mass transfer. I'll give you more information in a minute. So what about the first equation, the general equation of mass transfer? This equation has different terms, different elements. When we consider a steady state, we can cancel one of these terms, the concentration of element A over dt. We can say that this is equal to 0. This is the main difference from unsteady state and the cases that we covered in previous classes. In this particular case, there is dependence with time, so we cannot cancel this term in equation number 1. The rest of assumptions could be very similar. So, well, in previous lectures, we consider there is only one direction. So that simplifies a lot the solution, the mathematical solution of this equation. And also, we saw different cases when this term A is equal to 0, when there is no chemical production. What about equation number 2? The equation number 2, again, in previous lectures, we covered 3 different cases. And in the case of unsteady state, it would be exactly the same. When there is unimolecular diffusion, that is when one of the elements is stagnant, that is, that it doesn't diffuse. Second case is the steady state diffusion, when there is a, let's say, a boundary condition that is moving. If you recall, we talk about and we gave an example of a beaker that the level of the element A was moving with time. And the third case is the equimolar counterdiffusion, when the flux rate of the element A is equal and in the opposite direction as the molar flux of the element B. And this is exactly the same in the case of unsteady state. When we combine equation number 1 and equation number 2, this is the general equation box in green that we will need to solve. I mentioned initial conditions and boundary conditions. Assuming, let's say, the most simple geometry, which is a plate, and also relatively simple initial conditions, that is when time is equal to 0, the concentration has a value of initial concentration, and as a boundary conditions that when x is equal to 0, the concentration has some value, and with x is equal to L, the concentration has the same value. Under those conditions, if we try to solve this equation, we'll see the analytical approach. And again, it's not going to be easy, even considering, let's say, a very simple geometry and a relatively simple initial condition and boundary conditions. We're going to follow the same methodology that we covered already in the case of heat conduction. And the reason why is that, well, if you take a look to the general equation of unsteady state heat conduction, you can see the similarities. The equation looks very similar. Also, we can define initial conditions and boundary conditions very similar as well. So if you recall, in heat conduction, we also saw two different approaches. One is the analytical methodology, in this case for unsteady state conduction. We can also use numerical methods, like for instance, MATLAB or any other software. But in any case, it will imply the mathematical solution of the general expression. The second approach would be the use of graphical method. So there are different graphical representation that we can use to solve the problem. This is normally an estimation. Maybe it's not that accurate, but for practical purposes, the use of these highest layer charts are very good, very practical. So how can we analytically solve this equation? Well, first, we need to simplify the partial differential equation, which is way more difficult in most of the cases, more difficult to solve than the ordinary differential equation. So first, we need to simplify the partial differential equation as much as possible. Then we need to try to convert this partial differential equation to ordinary differential equation, and there are different methodologies to do so. Third, we need to determine the value of the constant when we solve this ordinary differential equation. 4 boundary conditions and 5 initial conditions. So, well, this is the general methodology, and in the case of that particular equation and considering the initial conditions and the boundary conditions defined a few minutes ago, we can use the solution calculated for the case of the heat conduction, and because we saw already that there are many different similarities, and in this case you can see here in the slide what will be the solution. It's clear that this is not a very simple methodology, that it involves a lot of calculation and mathematical assumptions. I mean, it's not easy. So in order to avoid that, we're going to see in a minute what will be how can we use these charts that I mentioned at the beginning of the presentation. And we're going to see different geometries. For each of the geometry, there is an associated chart. If you take a look to the Appendix F in your textbook, we define 4 different parameters when it comes to unsteady state. The parameter y, the parameter x, the parameter n, and the parameter m. When we cover heat conduction, we define these 4 parameters as a function of the temperature and time. Also as a function of the relative position and the relative resistance. In the particular case of heat conduction, it was related to the convection heat transfer and conduction heat transfer. In this case, in mass transfer, we're gonna use a similar approach, but instead of talking about temperature, we're gonna talk about concentration. And also we're gonna talk about diffusion instead of alpha. And for the resistance, we need to incorporate diffusion and mass transfer coefficient that we cover in lecture 14, I believe. But the procedure will be the same as we've seen already in heat conduction. We will need to calculate 3 out of these 4 parameters, and then we're going to use the graph to determine the value of the last parameter. And with that, we're going to be able either to calculate time or what's the final concentration. So as mentioned, we're going to use the graphs in Appendix F. And in the case of mass transfer, we need to determine the value of the relative concentration change. There is a typo here. Relative time, relative position, and relative resistance. In my experience, what is tricky here, and some students fail, is the calculation of the relative position, the parameter n. In each of the graphs, there is an indication of the value of x1, and that we need to consider in order to calculate the value of this parameter n. I'll give you a few examples in a minute. This is the case of the large flat plate that you have in the Appendix F in your textbook. The elements y, x, n, and m. And it's important, as mentioned, to know what's definition of x1. So x in this particular case is the value from the center of the flat plate to whatever the position we are calculating the concentration. While in this case, x1 is equal to half of the thickness of the plate. Okay, so once we calculate, let's say, y, n, and m, we get into the chart, and depending on the value of x, m, and n, we can, depending on the value of y, m, and n, we can get into the chart and calculate the value of x. With the value of x, we are able to determine the time, and vice versa. If we know x, using m and n, we're able to determine the value on y, and therefore the concentration. So it's exactly the same as we saw in heat conduction. We just need to switch the temperature by the concentration and alpha by the diffusivity, DAB. I wanted to give you let's say a particular case. Let's say that we want to calculate, there is a steady state, and we want to calculate the concentration after some time in a flat plate. But one of the faces is insulated. So there is no mass transfer going through that particular face of the plate. In that case, we can assume that the geometry is equal to this general case of large flat plate, but just ignoring half of the plate. So in this case, x1 will be exactly the same as the thickness of the flat plate, while x will be whatever the position, starting from the center. In this case, is not going to be the center, it will be the base of this flat plate, which has one of the sides, one of the faces insulated. Let's say that we want to calculate the concentration of the time in the center of this flat plate. In this case, we don't have to worry about the relative position. We just go directly to the graph that it says, well, the calculation in the center. In the case of the cylinder, well, there is a corresponding graph, the corresponding chart, and in this case, the x1 is equal to the radius. It's not the diameter, but the radius. So do not get confused when if you need to do the calculations and you need to calculate this relative position. Same way as in the plate, if the problem asks to calculate whatever change in the center, you can directly use this chart here. And finally, the sphere, the x1 is as well equal to the radius. And well, we use the same, we need to calculate the same parameters and use the corresponding graph. Same if we want to calculate the variation in the center, then we can directly use this chart here. Well, I mentioned that in most cases we're going to try to simplify the general equation and assume that there is one dimension. What happens if there is 2 or 3 dimensions? Same as we covered in heat transfer, we can, let's say, solve the problem in different steps, or considering the problem can be split in different sub problems. For instance, if there is this 3D graph, 3D geometry, we can calculate the value of the overall y as a function of the y over each of the faces of this parallelepiped. Saying if we have 2 dimensions, then the overall y will be equal to the y over the different faces, in this case A and B. Third case is when there is a cylinder, but we also want to consider the bases, the top and the bottom. And in this case, the overall y will be equal to the y related to the cylinder times the y related to the base, either the top or the bottom. And therefore, when we want to solve a system, a 3D systems, we need to do all the different assumptions and over the coefficient y. And once we calculate the coefficient y, considering this 3D geometry, the rest of the parameters will be exactly the same, or the way to calculate those will be exactly the same. This is just a summary. So when we have a rectangular bar with insulated ends, we can calculate the overall y as a function of the y over 2 of these faces, A and B. There is also an indication of the definition of the value of x1. If there is a transport in a rectangular parallelepiped, as we saw in a minute, the overall y will be calculated as a function of the y over the different faces A, B, and C. And x1 in the case of A will be equal to A. The coefficient B or the position x1 for the evaluation of the coefficient over B will be equal to the B. And for C, exactly the same, so x1 will be equal to C. If we want to calculate the transfer in a cylinder including both ends, then the overall y will be equal to the y related to the cylinder times the y related to one of the ends, where the y over this one of the ends, the definition we will need to use x1 equal to A. So in summary, in this lecture, we cover the general expression for unsteady state diffusion, which is here boxed in the green in a green line, and we saw that there are 2 different approaches to solve this general expression. One is the analytical solution that can be really complex depending on the geometry, the initial conditions, and the boundary conditions. And secondly, the second approach will be to use this graphical representation and solve the equation for 3 different geometries, which, as you have seen, is much more easier than the analytical solution. In general, for this course, what we're going to use is the Heisler charts. So we won't pay too much attention to the analytical solution. This is more related to mathematical skills and mathematical solution than heat and mass transfer, and therefore the focus gonna be more in the what is specific to mass transfer, and in this case the Heisler charts. Okay, so if you have any questions, you can reach me by email, and this is my email address. Thank you very much.